Have you ever stopped to think how your robot vacuum or even a self-driving car can just figure out a room it's never been in? How does it do that? Well, the secret sauce is this incredible concept called SLAM. That stands for Simultaneous Localization and Mapping. And we're going to break down exactly how it works.
So, to really get a feel for this, let's try a little thought experiment. Imagine you're suddenly lost in a thick forest. It's pitch black, and all you have is a flashlight. No map, no compass. To find your way out, you've got to figure out where you are, right? But to do that, you have to start building a mental map of your surroundings. And to build that map, well, you need to know where you are while you're making it. See the problem?
This right here, this is the fundamental question. It's the puzzle that SLAM was invented to solve. It's a challenge that robots have to deal with constantly. So how on earth do they pull off this seemingly impossible task?
Well, here's our game plan. We're going to start with what I like to call the robot's existential crisis. Then we'll break SLM down into its 5 key parts. We'll look at the early attempts to solve it, and then the modern revolution that changed everything. We'll get into the real magic, something called loop closure, and finally, we'll see how this stuff actually works out in the real world.
All right, first up, the robot's existential crisis. And really, this is just a perfect way to describe the core chicken and egg problem of SLAM. So this image right here, it perfectly captures the paradox. To know where you are, that's localization, you need a map, right? But to build that map, you have to know where you are when you're making it. It's this total catch-22. And you can see how things could go wrong fast. A tiny mistake in your location messes up the map, and a messed up map means your next location guess is going to be even more wrong. It's a vicious cycle. So how do you possibly break a circular problem like that? Well, you build a system with different parts that all talk to each other. So let's pull apart a SLAM system and look at the 5 essential pieces.
You should think of this as a constant cycle. First, the robot senses what's around it. At the same time, it uses odometry, basically counting its wheel turns, to guess how far it's moved. Then comes data association, where it tries to go, have I seen that corner before? All that info feeds into the mapping part, updating its picture of the world. And then, the most important bit, loop closure. That's the aha moment when it knows for sure it's been somewhere before. And this is a great illustration of how this isn't just a step-by-step thing. It's not linear at all. These 5 pieces are in a constant feedback loop. Data is always pouring in from the sensors and the wheels, and the system is constantly tweaking and improving both the map and its own location on that map all at once.
Now this was not an easy problem to solve. Let's rewind a bit and look at the first attempts to figure this out, which were all about wrestling with probability.
Yeah, so one of the first big breakthroughs was called EKF-SLAM. The idea is as the robot moves, it gets more and more unsure about its exact position. That's the big, expanding oval you see. But when it spots a landmark it already knows, it can use that to shrink its uncertainty. The huge downside, it had to keep track of how every single landmark related to every other landmark. That meant the math just exploded, making it way too slow for big spaces.
So the next big step forward was FastSLAM. This was a clever solution. Instead of one single super complex guess, it basically threw out a whole cloud of particles. Each of these little particles represents a possible reality, a different path the robot might have taken. And here's the key. Each particle only had to manage its own simple little map. The system could then just focus on the most probable particles, which made mapping huge areas suddenly possible.
But the true game changer, the thing we use today, came from looking at the problem in a completely new way. And that brought us the modern revolution, graph SLAM.
Okay, so this is the fundamental difference. The old way, the filtering way, would look at new sensor data, update its guess, and then basically throw the old raw data away. The modern way? It keeps everything. It looks at the robot's entire journey, from start to finish, all at once, and asks, what is the one single path that makes the most sense of everything I've ever seen? And this is what it looks like. We turn the robot's path into a graph. Each of those blue circles, the nodes, is a spot the robot stopped and took a look around. The blue lines, the edges, are its movements between those spots. This whole thing is a complete record of its journey, just sitting there waiting to be optimized. Which brings us to my favorite part, and honestly, the most critical piece of modern SLAM. It's the part that feels like actual magic. It's called loop closure, and it's all about fixing your past mistakes. So check out the top part of this image. It doesn't matter how good your sensors are. Every time a robot moves, there's a tiny, tiny error. Over time, these little errors pile up. We call this drift. And on a long trip, like driving around the block, the drift gets so bad that when the robot gets back to where it started, it doesn't line up.
The map is broken. It's inconsistent.
Okay, but now look at the bottom half. This is the magic trick. The robot recognizes a place it's been before. It closes the loop. This adds a super powerful new connection to our graph, a constraint, linking its current spot to a place it was way back at the beginning. An optimization algorithm then just kicks in. It pulls and stretches the entire path to make that one new connection fit perfectly. And bam, the whole map just snaps into place. It becomes correct. It's honestly one of the coolest things in robotics.
So that's the theory. It's pretty cool, right? But how do you actually put this to work with real robotic software?
In a modern setup like ROS, the robot operating system, you'll have this central component called a SLAM node. All the raw data from sensors like cameras and lidars, plus the movement data from the wheels, gets piped into this node. It does all the heavy lifting, the graph building, the optimization, the loop closures, and then it spits out two vital things, the updated map and a much more accurate location for the robot.
And the great news is, developers don't have to reinvent the wheel. There are amazing open-source tools that do this. For example, if your robot is mapping a flat 2D space with a LiDAR sensor, SLAM Toolbox is pretty much the go-to. But if you need to map a complex 3D environment with a depth camera, then something like RTAB Map is an awesome choice. It actually uses what it sees to find those critical loop closures.
In the end, what's so cool about SLAM is that it isn't just one field of study. It's this perfect mix of geometry to understand shapes in space, probability theory to deal with all the uncertainty, and pure optimization to find the very best answer from a mountain of messy data. So, by solving this deep internal problem of where they are and what their world looks like, robots are finally free to really explore and operate within it. And that just leaves us with one final really exciting question. Now that they can build their own maps of our world, what do you think they're going to find?